Sometimes we have a value, or we actually have values. We have a value at one point in time, a value at a different point in time, and we know the length of time between those two points, and we want to find the implied rate that is associated with those two values. Common examples, if suppose we can make an investment today and it's going to pay us some certain amount of money at some certain point in time in the future, we can back out the implied rate. So if we had an investment where we give our broker $5,000 today and in 7 years we get back $12,000, we can figure out what's the rate that gets us from 5,000 to 12,000 over 7 years. Alternatively, we may have made an investment of a certain amount at some point in the past. Today, our account has a certain amount of money, and we can figure out what the implied rate of return is that we earned each period from when we made the investment to today. And you basically can view this either as a future value problem or as a present value problem. You're trying to solve for R, so if you have a certain amount today and you have a value at some point in the future and you know the length of time between those two, what's the R such that if you compound this by R for t periods, you wind up with this. Another way to look at it, kind of the present value way, is you have some value at time t, you know what its present value is, the length of time between the two measurements, and you want to find the discount rate such that if you discount the later value by this each year or each period for t periods, you'll wind up with this present value. And the financial functions on the calculator is particularly useful in solving these kinds of problems. So what you would give is if we want to view this as a future value, we give it the present value, and remember we give it the opposite of the value as of time zero. We give it as FV, we give it the later value. N is the number of periods, and again, we're assuming right now that we have no interim cash flows, and therefore mode doesn't matter, and the calculator will solve for I% per period. What's the rate so that if you had this at I%, it would get you to this. Alternatively, you can think of it as you give it FV, you give it PV, give it N. What's the rate? So if you discount this by I% per period, you'll get that present value. And again, remember your sign convention where PV is actually going to be the opposite of the present value, and FV is going to actually reflect that present value, or is going to actually reflect that value or that cash flow. You don't have to worry about or incorporate the sign convention with FV. So here's a case where you have an investment that you can buy today for $500, and in 5 years you'll double your money. You'll get $1,000. So one way to look at this is if I put in $500, what's the rate that I get each year for 5 years? 1, 2, 3, 4, 5. That'll get me to 1,000, and that's reflected in this equation. 500 times 1 plus r to the fifth is equal to 1,000. Alternatively, 5 years we get paid 1,000. We know it's currently worth 500. What's the rate that if we discount the 500? If we discount the 1,000 by for 1, 2, 3, 4, 5 years, we get 500. That's viewing it in a present value context. So we can go ahead and solve this. We have our initial value is 500, so remember you got to put the opposite of 500. FV is 1,000. It's as if we put in 500 and then we'll get back 1,000. What's the difference between those time-wise? 5 periods. Solve 14.87%. So you put in $500 today. If you were to earn 14.87%, you get 1,000 in 5 years. You can do this algebraically. 500 times 1 plus r to the fifth is equal to 1,000. And so you divide both sides by 500, so you get 1 plus r to the fifth is equal to 1,000 over 500, which is equal to 2. Take both sides to the power of 1/5, and so you wind up with 1 plus r is equal to 2 to the 1/5, which is 1.1487, and you get 14.87%. And again, here it was set up as 500 times 1 plus r to the 5th. Invest 500. What's r for 5 years to get you to 1,000? It looks very similar if you have 1,000 and you want to find the r that you discount for 5 years to get to 500, and you wind up with 1.1487, leading you to 14.87%. Another situation that we often have is where we have two values. We have the rate, and we want to find the number of periods between those two values. So common example, suppose you're going to make some investment today, or you have a certain amount of money today, and you have a target in the future, a savings target. You know what rate you can earn, and you want to know how many periods will it be before you hit your target. Another application is, I have an account with a certain amount of money. I know that I made an investment of a certain amount at some point in the past. I know the rate on that investment, and I want to know exactly when did I make that initial investment. How long ago, how many periods ago. So again, here we are finding T. I invest a certain amount. R percent per year is the return. FV at time T is my goal. What is T? What is the number of periods that I have to compound this to get to that? Likewise, I have my later value. I discount it. How many times do I need to discount it to get to that present value? Again, the financial calculator is going to be really useful. So we give it our present value, rate of I percent per period, and we know what the target is. We set that as FV, and will tell us the number of periods that it needs to grow. And this picture is drawn such that n is an integer. It doesn't necessarily have to be. Here, FV gives us our later value, and we want to know n such that if we discount it by I percent each year, it'll wind up having a present value equal to the opposite of what we put in for PV. So PV is going to be the opposite of FV. Or PV is the opposite of the present value of FV. So you need $20,000 to buy a car. You can get 10% per year, and right now you've got $15,000. How long will it be before you have enough money to pay cash for the car? So basically, you have $15,000, 10%, 10%, 10%, 10%. How many years of 10% is it going to take you to go from $15,000 to $20,000? So again, this is the problem you're solving for. You've got 15. You have an annual return of 10%. What's the T that'll get you to 20,000? A little bit less obvious is you have 20,000. You're going to discount by 1.1 per year, capture the 10%. How many periods is it? How many years is it? Such that when you discount that 20, you get to 15. So if I were to put in 15 today, take out 20 in the future, have an interest rate of 10%, solve for n, how long would it take to get there? A little over 3 years. You can solve algebraically. So you have your 15,000. Every year grows by 10%, and you want to know how many years it compounds before you hit 20. So you divide both sides by 15. You're stuck with that T up there as an integer, so what you need to do, I'm sorry, not an integer, an exponent. T is an exponent, and the way you can pull that out is by taking the log of both sides. So you take the natural log of both sides, and natural log of 20,000 over 15. Remember, the natural log of something to its power, you can pull the power out and bring it before. So T is equal to this expression, which is essentially what the financial calculator did. So how many T's to get from 15 to 20?